Hello and welcome to this revision session for A-Level Physics on the topic of mechanics on the concept of forces and motion, which is part of AQA Paper 1. So in today's lesson, if we've been successful, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? When you're completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. And in this section, write down your working out and answers to the questions in the revision session. When you're doing this, make sure to write in full sentences and show your full working out. Whilst in the right hand side, write down any bits of information which you find useful, any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising for AQA A-Level Physics? Well, the first step is to learn the key facts. Use revision guides, student prep books, class workbooks, the textbook to learn the key ideas of the course. Then test yourself. Use things like Caboodle, Seneca, the student knowledge checkers to quickly test your own knowledge. Then finally, use exam practice books, homework books, supervised study books, additional workbooks to answer exam questions and to mark your own work. So learn the key facts, test yourself, and practice exam style questions. So in this revision session, we're going to be looking at forces and moments. So what are the key facts to do with this? Well, a resultant force causes an acceleration. An acceleration is a change of speed or direction. The resultant force must be considered in both horizontal and vertical planes. The resultant force is equivalent to mass times acceleration, which is Newton's second law of motion, F equals ma. We know that a resultant moment will cause an object to rotate. If the moments are balanced on an object, the object will be balanced. A moment is the force times by the perpendicular distance, and a couple is a pair of forces that act in opposite directions, perpendicular to each other with the same magnitude, but will produce a resultant moment. Now, the weight of an object always acts perpendicular down from the centre of mass, which is called the line of action, and the centre of mass is assumed to be at the centre of the object. Now, an object is in equilibrium if there's no resultant moment or resultant force. So let's have a look at some key check questions to do with forces and moments. So our first question says, calculate the magnitude and the direction of the resultant force. So to work out this answer, we say r squared is equal to 2 squared plus 3.1 squared. So therefore r squared is equal to 13.6, so r is equal to 3.7 newtons. We can then say tan theta is opposite over adjacent, so it's going to be 3.1 over 2, which is 1.55, so our angle of theta is 57 degrees. So the resultant displacement is 3.7 newtons at 57 degrees from the horizontal. Calculate the magnitude and the direction of the following resultant force. So we do r squared is equal to 6 squared plus 16 squared, so we get 292. So therefore r is equal to 17.1 newtons. Tan theta is equal to opposite over adjacent, so 6 over 16, which is 0.38. So theta is equal to 21 degrees. So our resultant displacement is 17.1 newtons at 21 degrees from the horizontal. Calculate the magnitude and the direction of the following resultant force. So the first thing we know is that overall in the horizontal, the force is 1 newton. So therefore r squared is equal to 1 squared plus 1 squared. So r squared is equal to 2. So r is equal to 1.4 newtons. Tan theta is opposite over adjacent, which is 1 over 1. So theta is equal to 45 degrees. So our resultant displacement is 1.4 newtons at an angle of 45 degrees from the horizontal. An aircraft is flying due north with a velocity of 200 meters per second. A side wind of velocity 50 meters per second is blowing due east. What is the aircraft's resultant velocity? So we can say v squared is equal to the vertical velocity squared plus the horizontal velocity squared. So it's 200 squared plus 50 squared, which is 42,500. So therefore v is equal to 206 meters per second. Tan theta is opposite over adjacent, which is 50 over 200, which is 0.25. So theta is therefore equal to 14 degrees. So the aircraft's resultant velocity is 206 meters per second at 14 degrees east of north. Figure 4 shows a meter rule pivoted at its 50 centimeter mark. Two objects of weight 0.70 newtons and W are placed on the ruler as shown to balance it. Assume that the weight of the ruler is negligible. Calculate the size of W. So we know that W is going to be equal to moment over distance, because we know moment is equal to force times by distance. So therefore, what is our moment? So our moment is equal to 0.7 times by 0.32 from the other side of the balance point, and they'll balance out because it's in equilibrium. Then we divide that by 0.14 because we turn centimeters into meters, 1.6 newtons. With the same idea, calculate the force acting on the pivot. Now we know, because it's balanced, it's in equilibrium, that the forces up must equal the forces down. So we can say R is equal to 0.70 plus 1.6, which is therefore equal to 2.3 newtons. Figure 5 shows a model of a loaded section of a bridge made using a uniform wooden beam. R of beam is working it through. Now the wooden beam is 120 centimeters or 1.2 meters long and has a weight of 15 newtons. One end of the beam rests on a support and the other end is fixed to a vertical string. Calculate the vertical force R at the support. So we know that the moments are balanced about the point. So if we take our moments from point A, we can say R times by 1.2 is equal to 15 times by 0.6 plus 13 times by 0.40. Again, we turn our centimeters into meters. Therefore, R is equal to 142 over 1.20. It is equal to 12 newtons. With that same idea, calculate the vertical force T. Once again, we know upwards forces equals downwards forces. So we can say upwards is 12 plus T is equal to the downwards, 13 plus 15. So therefore T will equal 16 newtons. The next question says, explain the following observation. Two people can balance a seesaw even if one is much heavier than the other. Well, the moments can be equal. As the lighter person produces a smaller force, they would need to sit further away from the pivot to generate a moment of equal size. Explain the following observation. It is easy to undo a tight screw using a screwdriver with a large diameter handle. A large diameter handle provides a greater turning effect and hence a greater force on the screw. Old buses and lorries had large steering wheels. Well, old buses and lorries had no power steering, so the large radius of the wheel amplified the turning effect or the moment that was taking place. A windsurfer stands on a windsurf board and holds onto the sail as shown. As the force from the wind increases, the windsurfer leans back further. Explain how leaning back further keeps the windsurfer in equilibrium. Your explanation should make reference to moments. The force from the wind produces an anti-clockwise moment about the point where the sail attaches to the board. So the weight of this windsurfer produces a moment in the opposite direction. So the windsurfer leans back until the moment due to his weight has increased to equal the increased moment of the wind force. Describe the motion of this object. It will accelerate to the right as there's a resultant linear force to the right, and it will spin in a clockwise direction. As you can see, that it's going to cause rotation in a clockwise direction. Describe the motion of this object. It will spin in an anti-clockwise direction. The linear forces cancel through, but the rotational forces will not. Is this a couple and why? Yes, the forces are equal in size, perpendicular to each other, opposite in direction, and will cause a resultant moment. Is this a couple and why? No, as the forces are all acting in the same direction. Is this a couple and why? No, as all the forces are not equal in size. Is this a couple and why? It's not a couple, as the forces are different magnitudes and they're acting in the same direction. Is this a couple and why? It is a couple, as the forces are the same magnitude, share the same perpendicular plane and are acting in opposite directions. Is this a couple and why? Yes, it is a couple, as the forces are the same magnitudes, they share the same perpendicular plane, and are acting in opposite directions. Is this a couple, and why? It is not a couple, as there's only one force producing a moment on the object. Is this a couple, and why? It is a couple, as the forces are the same magnitudes, share the same perpendicular plane, and are acting in opposite directions. Is this a couple, and why? It is not a couple, as the forces are different magnitudes. Is this a couple, and why? It is not a couple, as the forces are acting in the same direction. Is this a couple, and why? It's not a couple, as the forces have different magnitudes. So let's have a look at some exam style questions to do with forces and moments. A rescue worker is pulling a 25 kilogram sled of equipment up a smooth, icy slope inclined at 18 degrees to the horizontal. She pulls the sled using a rope angled at 30 degrees to the slope, applying a tension of 120 newtons. Assume there is no friction and the sled moves at a constant velocity. Show that the component of the sled's weight parallel to the slope is approximately 75 newtons. Resolve the 120 newton tension into components parallel and perpendicular to the slope, and then use the answers to assess whether the rope is providing sufficient force to keep the sled moving at a constant velocity up the slope. So pause the video now, then unpause the video when you want to go through your answer. Right, we can know that the weight is equal to mass times by gravity, so therefore it's 25 times by 9.81, so it's 245.25 newtons. Now the component down the slope is going to be the vertical component, so we can say it's W sine theta, where the theta is the angle with the horizontal. So therefore W sine 18 is going to equal 245.25 times by sine 18, which is 75.8 newtons. Now to resolve the tension, we can work out horizontally, which is going to be T cos theta. So it's going to be T cos 30, so it's 120 times by 0.866, which is 103.9 newtons. Whilst vertically, which is perpendicular to the slope, is going to be T sine theta. So it's going to be 120 times by sine 30, which is 60 newtons. Now finally, we can work out that the component of the weight down the slope from the first part is 75.8 newtons. The component of the tension up the slope, which you've just worked out, which is going to be along the slope, is 103.9 newtons. This tells us that the tension force is greater than the component of weight. So therefore, if it's moving at a constant velocity, there must be overall no resultant force. So therefore, there must be another force acting down the slope. Now, the motion, as we said, is at constant velocity, so our net force is 0. So therefore, we know the upward tension and the downward weight are going to be balanced, so our sled is going to be in equilibrium. Now, a horizontal maintenance platform of negligible mass is suspended in mid-air by two taut cables attached to a ceiling. Cable A is inclined at 35 degrees to the horizontal and exerts a tension of 620 newtons. Cable B is inclined at 50 degrees to the horizontal and in the opposite direction. A worker and the equipment stand on the platform, exerting a total downward force of 800 newtons at the centre. The system is in vertical equilibrium. Resolve the tension in cable A into horizontal and vertical components. By considering vertical equilibrium, calculate the vertical component of the tension in cable B, hence determine the total tension in cable B. Then assess if the system is in horizontal equilibrium. So pause the video now, then unpause the video when you want to go through your answer. Right, in our first one, horizontally, it's going to be T cos theta, so it's going to be T cos 35. So therefore, it's 620 times by cos 35, which is 355.9 newtons. Vertically, in this case, it's going to be T sine theta, so it's going to be 620 sine 35, so it's 508 newtons. Now we know that the total vertical support needed is going to be 800 newtons because we need our overall vertical force to be 0. So if downwards is 800, upwards must be 800. Now cable A, as we've just worked out, provides 355.9 newtons towards this. So cable B must therefore provide 444.1 newtons vertically. Now we know sine 50 is equal to F vertical over the tension due to cable B. So therefore cable B is equal to sine 50 times by this force, which is 444.1. So it's 580.1 newtons. For the final part of the question, the horizontal component of cable A, as we've just worked out, is 508 newtons. Now the cable B tension, if you work it through, is going to be 580.1 newtons, as shown in the previous question. So therefore 580.1 times by cos 50, which is the horizontal value, the horizontal component of cable B's tension, is going to be 372.8 newtons. So therefore the total horizontal force is not going to be equal to 0. It's actually got a force of 135.2 newtons towards the left, indicating that we're not in horizontal equilibrium. An engineering team is stress testing a uniform horizontal steel beam of length 3 metres suspended at its centre from a crane. They apply 2 vertical downwards forces at known distances from the centre, simulating uneven loads. The beam remains horizontal and stationary in each case. The data below shows 2 different test configurations. For test 1, show that the moments about the centre are balanced. For test 2, calculate the value of force B that we require to keep the beam in equilibrium. Then the engineering report suggests that a shift in the position of force A by 0.10 metres in test 2 would require significant recalculation of force B. Evaluate this claim and comment on the sensitivity of the balance conditions to position. So, pause the video now, then unpause the video when you want to go through your answer. Right, in our first question, we can say that the clockwise moment is equal to 210 times by 1 from the information given. So therefore it's going to be equal to 210 Newton meters. The anti-clockwise moment from the information given is 280 times by 0.75, which is 210 Newton meters. So the moments are therefore equal and opposite for test 1. So our total moment is 0. So therefore the beam is in equilibrium and remains horizontal. For the next question, the anti-clockwise moment is equal to 300 times by 0.60, which is 180 Newton meters. So we can set this therefore equal to the clockwise moment. So therefore FB times by 1.2 is equal to 180. So therefore FB is 180 over 1.2, 150 newtons. Now the new position of force A is going to be at 0.70 meters from the information given. So our new anti-clockwise moment is force times by distance, so it's 300 times by 0.70, which is 210 Newton meters. So our required clockwise moment to create an equilibrium is 210 Newton meters. So FB in this case is going to be 210 over 1.20, which is equal to 175 newtons. So when we compare this to the original, 150 newtons, which leads to a change of 25 newtons from a 0.10 meter movement on the actual object. So this indicates that the moments are highly sensitive to the distance. A small position change can require significant force adjustments for balancing the actual object. The next question says, an experimental drawbridge section is lifted horizontally using 2 hydraulic arms placed symmetrically 2.4 meters apart and mounted to apply equal and opposite forces. Each arm exerts a vertical force of 4.2 kilonewtons at the same perpendicular distance from the center line of the bridge deck. A 2,500 kilogram vehicle is accidentally left parked on the right hand side of the deck, causing the bridge to tip slightly before the arms are activated. The vehicle's centre of mass is located 3.6 metres to the right of the deck's centre. The hydraulic system is designed to hold the deck level by producing a couple to counteract the unbalanced moment caused by the vehicle. Firstly, show that the unbalanced moment due to the vehicle about the centre of the deck is approximately 88.3 kilonewton meters. Calculate the perpendicular distance from the centre of the deck to each hydraulic arm if the couple they produce exactly balances this moment. Then discuss how the concept of a couple allows this system to remain stable without producing a net linear force. Evaluate why a couple rather than a single counteracting force is necessary. So, pause the video now, then unpause the video when you want to go through your answer. In our first question, we can say that the weight of the vehicle is mass times by gravity, so it's 2,500 times by 9.81. So the value for the weight is 24,525 newtons. Moment is force times by distance, so we multiply this by 3.6 meters, so we get a moment of 88,290 newton meters. Next, we know that the total moment is 2 times by 4.2 kilonewtons times by x, where x is the distance from the centre to each arm. So 2 times by 4.2 times by x is equal to 88.3. So x is equal to 88.3 over 8.4. Remember, we can just cancel through these kilonewtons. Okay, so therefore it is 10.51 meters. So this indicates to us that each arm must be 10.5 meters from the centre to balance the moment. Now we know that a couple will produce rotation only. The equal and opposite forces in the couple cancel linearly but will produce a net torque. So this setup avoids pushing the bridge either sideways or upwards. So a single upwards force from one hydraulic arm would produce both rotation but also lift. So in this scenario, the symmetrical couple ensures that the bridge will rotate to a level position without shifting its support base either up or down or side to side. Figure 4 shows an archer using a bow in a competition. The archer exerts a force F to pull point P on the string back through a distance S. Figure 5 is a simplified diagram of the bowstring showing the forces acting on P. The tension in the string is T and the string makes an angle of 75 degrees to the horizontal. In figure 5, F is 160 newtons and P is in equilibrium. Calculate T. So, pause the video now. Then unpause the video and you want to go through your answer. Right, we know that if it's in equilibrium, that F must equal 2 times by T cos 75, because we can see in the right hand side there's two forces acting on the right hand side to cause that equilibrium, so it's be 2 T cos 75. Now we know that F is 160, so 160 is equal to 2 T cos 75, so therefore T is equal to 310 newtons. Consider a ladder that a person can use to climb into the roof space of a building. When not in use, the ladder is stored in the roof space and the opening to the roof space is covered by a board. The board is hinged to the ceiling at one end. The ladder is attached to the board by a rail as shown below. A small block prevents the board from rotating into the roof space. The weight of the board and the rail is 50 newtons. The weight acts at a distance of 0.45 meters from the hinge as shown. The total length of the ladder is 2.70 meters with a 0.85 meters to the left of the hinge. The weight of the ladder is 54 newtons, assuming the ladder is uniform. So firstly, explain why the board and the ladder remain in the position shown. A downward force is required to rotate the board away from the block. This force is applied 0.80 meters from the hinge. Determine the magnitude of this force. So, pause the video now, then unpause the video and you want to go through your answer. So we know that the distance from the hinge to the centre of gravity of the ladder is going to be 2.7 meters. So therefore, what we can therefore say is divided by 2 or 2 minus 0.85 meters. So therefore, our clockwise moment is equal to 54 newtons times by 0.50, which is 27 newton meters. The anti-clockwise moment is 50 newtons times by 0.45 meters. So it's 22.5 newton meters. This indicates to us that the clockwise moment must be greater than the anti-clockwise moment. So therefore, the block will cause a force and a resultant moment. So it will cause a force or a moment. So therefore, our resultant moment, on the board and the ladder is 0, explaining why we'll stay in that same position. Now we know that the resultant moment must therefore be 27 newton meters minus 22.5 newton meters, which is 4.5 newton meters. We know that force is equal to the resultant moment over the distance away from the center of mass, or the rotation point, so therefore it's 5.63 newtons. Two brackets A and B support a shelf of length 1.2 meters. Bracket A is positioned 0.15 meters from the left-hand end of the shelf. A book is placed 0.35 meters from the left-hand end of the shelf as shown. The normal contact forces of each bracket on the shelf are equal. Determine the distance of bracket B from the left-hand end of the shelf, where the weight of the book is 8.5 newtons and the weight of the shelf is 14 newtons. Bracket B is moved closer to the left-hand end of the shelf. Explain the effect on the magnitude of the normal contact force of bracket B on the shelf. So, Pause the video now, then unpause the video when you want to go through your answer. Right, so there's a couple of ways we can work this through. We know that the total force up equals the total force down. So FA plus FB is equal to 22.5 newtons. Now we know FA equals FB, so 2F is equal to 22.5 newtons, so each F is 11.25 newtons. Now you can take your moment from either the left end, the midpoint, or taking it from A. So let's just take it from the left end because that's the easiest to work out. So we know if we take the moments from the left end, we know that the moments on the clockwise moments must equal the anti-clockwise moments. So 11.25 times by 0.15 plus 11.25 times by x is equal to 8.5 times by 0.35 plus 14 times by 0.6. So therefore x equals out to be 0.861 meters. Now, in this next question, if we move the bracket closer, the moment must be the same. So if there's a smaller distance, well then the force, because moment equals force times by distance, must increase. Now, two brackets C and D support a shelf of length 1.5 meters. Bracket C is positioned 0.25 meters from the left-hand end of the shelf. Vase B is a vase is placed of 0.45 meters from the left-hand end of the shelf. The normal contact forces on each bracket on the shelf are equal. So, determine the distance of bracket D from the left-hand end of the shelf, with the weight of the vase being 12 newtons and the weight of the shelf being 18 newtons. Then, bracket D is moved closer to the left-hand end of the shelf. Explain the effect on the magnitude of the normal contact force of bracket D on the shelf. So, pause the video now, then unpause the video when you want to go through your answer. Once again, it's the same principle. So we take moments about bracket C to eliminate the need to consider the force exerted by C in the equation. So the position of the vase from bracket C is 0.45 meters minus 0.25 meters, so it's 0.20 meters. The moment due to the vase about C is 2.4 Newton meters. Now the centre of mass of the shelf is located at the midpoint, so it's 0.75 meters from the left-hand end. So the distance from bracket C is 0.75 minus 0.25, which is 0.50 meters. The moment due to the shelf is 18 newtons times by 0.50 meters, or 9 Newton meters. Now, since the normal contact forces are equal, the force on bracket D is also the same as that on bracket C. So we know that the moments must balance. So FD times by the distance from C to D is equal to the moment due to the vase plus the moment due to the shelf. So it's going to be equal to FD times by D is 2.4 Newton meters plus 9 Newton meters, which is 11 Newton meters. Now, given that our normal contact forces are equal, we know that FD is equal to 12 plus 18 over 2, which is 15 newtons. So therefore D, the distance, is going to be the moment, which is 11.4 Newton meters, divided by our force, 15 newtons, to give our answer 0.76 meters. So therefore the distance of bracket D from the left-hand end is 0.25 meters plus 0.76 meters, which is 1.01 meters. Now, moving bracket D closer to the left increases the load it supports, as it's closer to the vase and the shelf's centre of gravity. Now, with bracket D being closer to the left end, it now has to support a greater proportion of the total weight. So this will increase the normal contact force on D. So as bracket D takes on a greater load, the force on bracket C decreases as it's now further from the centre of mass of the loaded shelf. A balance is formed by a beam suspended from a string. A dish is hung from the beam, and the balance is used to measure a fixed portion of rice. When the dish contains one portion of rice, the balance is in equilibrium. State the conditions needed for an object to be in equilibrium. Then the dish is moved along the beam so that the horizontal distance from the string to the dish is 7 centimeters. Rice is added to the dish until the balance is in equilibrium. Deduce whether the dish now contains 3 portions of rice. You should include a calculation of the weight of one portion of rice. The weight of the beam is 3.1 newtons and the weight of the empty dish is 0.64 newtons. So, pause the video now, then unpause the video when you want to go through your answer. Now, for an object to be in equilibrium, there are 2 conditions. The resultant force on the object is 0, and the resultant moment about the object is also 0. Now, for the next question, we know that the moment of the weight of the beam is 3.1 newtons times by 0.08 meters, which is how far it is from the center as shown in the diagram. So that's 0.248 newton meters. So we know that the moment equals force times by distance, so it's 0.248 equals the weight times by 0.25, so our weight of the dish and the rice is 0.248 over 0.25, which is 0.992 newtons. So the weight of one portion of rice by itself is 0.992 minus the weight of the empty dish 0.64, which is 0.352 newtons. So we know that moments on either side must balance. So moments are equal to 0.248 equals the number of portions times by 0.352 plus 0.64, the weight of the rice on the dish, times by 0.07. So we work it all through, we get our value to be 8.2. So the dish contains 8.2 portions of rice, not 3 portions of rice. A student abseils down the outside of a building using a rope. The mass of the student is 55 kilograms. The rope of negligible mass is attached to a fixed point X at the top of the building. The rope makes an angle of 15 degrees to the building. Firstly, calculate the weight of the student. Then determine the tension T in the rope. Then as the student abseils down the building, the angle the rope makes with the building decreases. State whether the tension in the rope increases, decreases or stays the same and justify your answer. So, pause the video now, then unpause the video when you want to go through your answer. Okay, we know that weight is mass times by the gravitational field strength. So it's 55 times by 9.8, which is 540 newtons. We can see from the diagram that the vertical value of tension is going to be T cos theta because the angle is being made with the vertical, not the horizontal. So 540 equals T cos 15. So therefore T equals 560 newtons, as shown in this diagram. Now, as the student abseils down the building, the value of tension will decrease because as the angle decreases, the cosine of the angle increases, or we could say the horizontal component of the force decreases. So therefore, this value of tension must decrease. So this brings an end to our revision session today. So if we're being successful, we should be able to answer A-level physics examination style questions, assess our understanding on A-level physics, and understand what topics we need to improve upon for A-level physics. So thank you for watching this revision session in the mechanics topic of AQA A-level physics on paper 1, looking at the concept of forces and moments. Thank you so much everyone, and as always, have a lovely day.